Now at this stage, let us try to classify the robots. We can classify robots in more than one ways. The first one we will use is with respect to its mobility aspects. Can the robot move or they are stationary? Manipulators are robots which are anchored to the workplace. Many of the industrial robots are this type of robots, manipulators. In the video segment, in the earlier hour, we saw the robots in industrial environments. These are manipulator types of robots because they are anchored. They do not move. They just make, they do not, they are not mobilized. They move, but their moves are restricted to a certain location. If we give the motion capability of these robots, then we call them mobile robots. If the robot, for instance, the Curiosity robot is a mobile robot. It has the capability of motion. But Curiosity robot is also a hybrid robot because it can move. It has got the motion capability, but also it has got an arm. Arm is fixed to its body, so it is anchored to the workplace. It is anchored to the workplace. But the robot itself is a mobile robot. Curiosity, we are talking about Curiosity. So we call this type of robots hybrid robots. Now look at, remember the robots in Expo 2005, the Honda Osima robot or Sony's robot. They are humanoid robots. They are also hybrid robots because they both have the motion capability and they also have manipulators which are attached to their body. So this type of robots are hybrid robots. So let's summarize. According to the mobility aspects, robots can be classified into three groups: manipulators, mobile robots, and hybrid robots. An industrial robot is usually a manipulator robot. A robot like the Curiosity on Mars is a hybrid robot, or a humanoid robot like Honda's Osimo is also a hybrid robot.
Hocam, I couldn't quite get the difference between mobile robots and hybrid robots.
Okay, the mobile robot, if the mobile robot can just move, but does not have a manipulator, for instance, an arm, you just call
okay,
it.
okay.
For instance, an autonomous car is a mobile robot because it doesn't have a attached manipulator to its body. But a Curiosity robot, Curiosity type of robot, which has got both the motion capability and the manipulator attached to it, is called a hybrid robot. Okay, is it clear now?
Yes, it is. Thank you so much.
Thank you for asking the question. Okay, humanoid robot. Let's look at Webster's dictionary, which gives the following definition. A robot is a machine in the form of a human being that performs mechanical functions of a human being. Okay, Webster's dictionary is not actually giving the definition of a robot, but it is giving the definition of a humanoid robot. Okay, What is the difference of a humanoid robot from a robot? Is that it should be in the form of a human being. A robot does not have to be in the form of a human being. It can be in the form of an animal. It can be in the form of a car or anything else. Or it may be in the form which we did not see before. But if we are going to call it a humanoid, it has to be in the form of a human being. So here you see a humanoid robot. It looks like a human being. Also, it has the gestures like human being. So it answers the gesture or the salute of the secretary in this is in a company in Japan, and this is the Japanese robot, and you see it responds. This is the Honda robot. You can see the name Honda here. A Honda Asimo robot responds to a human being. So this is a humanoid robot. Now they can have many of the functions of human beings, like they can walk. Although I have put these links here, these are some old links. You may not find this walking robot exactly at this link, but you can find many walking humanoid videos in YouTube. Running humanoid. Again, I cannot guarantee you can find it here because this is an old thing, but running, when you type in running humanoid into the search box of YouTube, you can see many running humanoid videos. Talking humanoids, dancing humanoids, and now after seeing enough of humanoid examples, let's come back to the first classification, which is the manipulator. We said manipulator is a robot which is anchored to a workspace. Here it is anchored. Its base is anchored here. It does not move. So it makes motions with respect to this anchored base. Now, it is we start into some of the terminology and taxonomy of robotics. So you see here some letters and some arrows, circular arrows, linear arrows, and two letters, P and R. I think you can guess what they are. R definitely comes from rotation, but it doesn't mean rotation. It means revolute here. Revolute is the joint which allows this link to rotate. So this is called revolute joint. So this term is this R is saying to us there is a revolute joint here. As you see, like human arm, robot arm is also composed of two basic ingredients, joint and link. And what type of joints do we have in our human body? All the joints in the human body are revolute type of joints. We cannot elongate our arm, so we do not have a prismatic joint. So the second term here is prismatic. So it allows this arm to move linearly. So this is the prismatic joint, and this comes from, P comes from prismatic. Okay. So think of human arm. How many joints do we have in human arm? We've got two joints. One at the joint, which is joining the arm to our main body. And the other is joint, which is which is connecting upper arm with the lower arm or forearm. So these two joints we have in the arm. First, here you can see that I've got more joints. So that means I can make a mechanical arm which is more dexterous or more capable of making different motions than a human arm. Because I can put the joints like prismatic joints, which did not exist in the human body. So, of course, the first designers of robot arms or manipulators took the model of human arm as the starting point, but they added some additional capabilities to it. So the part at the end, you can see here also you can understand that this is a wrist hand. Altogether, we have got 6 joints. So these 6 joints enable the robot make 6 independent motions. The number of independent motions we call degrees of freedom, and we are going to come back to these definitions later, but just now keep it in your ear. The degrees of freedom, how many independent motions a robot arm can make. Now think of an object in space. How many independent motions, for instance, an object in space, an aircraft? How many independent motions can an aircraft make? It can move in 3 directions, X, Y, and Z, and it can rotate about these 3 coordinates, X, Y, and Z. In other words, an aircraft in air or any object in air can make 6 basic motions. So that's why 6 is important. With 6 independent motions or 6 degrees of freedom, you can almost make any motion in space. So this is quite a capable robot with 6 degrees of freedom. Okay. Here now you are a fourth year student, and remember then that when you started in the when we first met in the second year in the computer graphics course, the first computer graphics course, I said to you that an engineer has got 3 languages. Do you remember what they were? The first one is obviously English, because the English is the language of all engineers in the world. The second is mathematics. We cannot have engineering without mathematics. The third is graphics. Look here now, we learned how to make basic graphics by using AutoCAD or any CAD program. Here you see an example of this. I will not be able to explain to you what this manipulator is if I did not have this graphics. So graphics is an important part of engineering language, together with English and mathematics. So we said that in designing robotic manipulators, human body is taken as an example, as a model. Now, what do we have in human body? We have joints. So in robotic mechanisms also we will have joints. And we already have seen that we can have even more number of joints or more variety of joints than the human body. And links, the parts which are connected by joints are called links. Now, we said that mathematics is an important part, one of the three ingredients of engineering language. Now, here comes frames of reference. Frames of reference is important because we define everything in engineering with respect to a reference. So for instance, when we define the position, where is my robot? With respect to what? So first, I should define a frame of reference. And here we are going to see something different that we haven't seen before. Because in other courses we had seen so far, we had one frame, it was fixed. Usually we fix it on the surface of Earth. And we call it, or we did not call it anything, we just called it reference. But now we are going to call it Earth-fixed reference. Because we are going to have another reference frame in robotics. We are going to have more than one reference frame. That's why I used the term not frame of reference, but frames of reference. So let's stop here now with that much information. Now, in robotics, we talk about frames of reference because we are going to have more than one reference. So if we have more than one reference, we will need a transformation between them. Now here the term is transformation between links, because one link may have another reference frame different from the previous link or the later link. Because we are going to see that these frames of reference are usually based upon links. So that means we are going to need to make transformation between links. How do we make transformations? Mathematical transformations. That's where the mathematics comes into play, into our help. And you have seen matrices. You have used matrices and vectors a limited amount, but you are going to see in this course that matrices and vectors are very important for robotics because these transformations are carried out using vectors and matrices. Now the last term here is kinematics of assemblies. Well, let's just keep this in our ear and let's wait until we define what kinematics is. Now, human body movement is a combination of many components. Likewise, we will see that robotics movement is going to be a combination of the components of robotic body movements. As we've said, like in human body, we will also have joints and a more varied number of and variety of joints we will have in robotics bodies. And you can see some examples here. Prismatic joints, flexible joints like you see here in this. Revolute joints, different types of revolute joints. And two joints define a link. Links are joined by, joints are linked by links. And end effector, we have hands. Whereas, I mean, this one here you see is very similar to human hand with fingers. But we can have many different types of hands. That's why a more common name of hand effector is used here. According to the function that you want from the robot, what comes at the end can have something different. So this is why it's called end effector. End effector is at the very end of the links what the final effect of the robot arm is applied. Okay, we classified the robots with respect to their mobilities, motion characteristics, like stationary manipulators, mobile robots, or hybrid robots. Now here we classify them with respect to their structure. This structure it is also what defines the workspace of a robot. If the robot is working in a Cartesian, a cubic workspace, it's called Cartesian robot. If it is working in a cylindrical workspace, it's called cylindrical. A spherical robot. Scara types of robot. This Scara type robot is also a cylindrical robot. Articulated robot. This articulated robot is also a spherical type of robot. Or a parallel. Now we are going to look closer to these. Now here again, you see the basic drawing, engineering drawing in defining these workspaces. I said cylindrical. Now here, by using engineering graphics, I use engineering graphics to show what I actually mean by a cylindrical workspace. In 3 dimensions from the top. So the robot actually covers if you look at it from the top, a part of a circle, but its height also may change. So defining a 3-dimensional workspace is as seen here. Whereas here it's a rectangular workspace. So the rectangular workspace, now remember that we defined 2 types of joints, prismatic and revolute. When I'm talking about rectangular workspace, I'm talking about a robotic structure which is only composed of prismatic joints. So I need 3 prismatic joints for a robot to cover a rectangular workspace. So I call it a rectangular robot. So look at this. Now to cover this partial circle, I need a radius, but I need to change this radius. So I want to cover anything inside this. So to change the length, we need a prismatic joint, but also I need to change the angle. To change the angle, I need a revolute joint. So with 2 joints, I can make a robot which covers this. But if I wanted to cover the cylinder, I am going to need another prismatic joint here. So you can see the joints here, with the arrows, prismatic, and revolute joint. So if a cylindrical robot, I can in short call PRP robot, prismatic, revolute, prismatic. So can you guess what a spherical robot is going to be composed of? Joint-wise. Joint-wise, then in the spherical robot, I am going to need 2 revolute joints and 1 prismatic joint. Here also, I need to be able to change the radius. So I can do this with prismatic joints. And I need to able to change the radius also like this. So this is, or I need to be able to rotate like this to make a sphere. So this is 1 revolute joint, also rotate circularly. So this is another revolute joint. So for the spherical robot, I will read RPR, that is revolute, prismatic revolute. So there's a question in chat. Okay. RR and P. Gone. Okay. Thank you for your contribution. Okay, now RPP. Khan, maybe you can ask your question orally. Use your microphone.
My room is currently a little loud, so that's why I didn't open the mic.
Can you repeat?
Currently, my room sometimes it's loud. My mom does cleaning right now, so I can't open the mic 24/7. I'm sorry.
So, ne demek? US ne demek? So can you open the question? What are you asking? RR ne demek mi diyorsun?
Ha,
R.
yok yok, oradaki şey önemli değil, ne demek anlamındaydı hocam. O şey değildi, hani soru anlamındaki değildi. O bir ufak bir yanlış anlaşılma olmuş.
Okay. So, thank you. PPP. What does it mean? Prismatic, prismatic, prismatic. What does it mean? It's going to have a rectangular workspace. How can I show it? I can write it. I can show it like this. But now I need a more simplified way of showing this as well. This is called skeleton type of showing. So when you see now this, now after taking this lecture, now you understand. It's a robot with 3 prismatic joints. So these show the prismatic joints. This is one way of showing the prismatic joint. Okay, so it can move in the X direction, Y direction, and Z direction, which covers the entire workspace. So we are going to use schematics, graphical representation, skeleton, graphical representation, or we can, if I just give the workspace to you now, you can tell me what type of kinematic structure, this is now called kinematic structure, the robot has got. So in time, we are also learning some terminology relate or taxonomy, informal terms of robotics. So kinematics is related to it is structure. This structure defines how, or kinematics define how the robot is going to move. RPP, we know now that it's a cylindrical robot. We can show it by one rotational or revolute joint and one translational or prismatic joint. So R R rotating about the base, R, which is this, P, which is this, and another P, which is this. Spherical robot. Look, here the prismatic joint is shown a different way. So there, I said to you, there are more than one ways of showing it. Okay, this is the prismatic joint as well. This is the revolute joint. And this is the prismatic joint. You see, in the same skeleton, two prismatic joints are shown by using different symbols. Both of them are prismatic joints, and this one is revolute joint. Here, revolute joint. This time is shown like this: revolute joint, prismatic joint. RRP. This is the SCARA type robot. And as I said, SCARA type robot is also a cylindrical type of robot. Now, think about the SCARA design is that the end effector moves parallel to the gravitational field, because we are going to see later when it comes to the control part. What makes robot control difficult is the nonlinear terms, and the nonlinear terms come from the arms which make angular movements against the gravitational field. So when we make angular motions against the gravitational field, terms like sine and cosine enter into equations. Sines and cosines are nonlinear terms. So nonlinearity you haven't seen yet in controls. And all the control you have seen is linear control, because we do not like nonlinearity in controlling systems. So here in this design, the designers said, well, let's not move in the gravitational field with an angle. So this is parallel to the gravitational field, whereas this arm moves perpendicular to the gravitational field. Okay, so cosine term disappears and sine term here becomes 1. So here it's parallel. So sine term becomes 0 and cosine terms becomes 1. So this way, the nonlinearity is avoided. That's why this type of design is given a special name, SCARA type of robot, and this is quite popular because it is easier to control.
Hocam bir şey sorabilir miyim?
Evet,
Bu biz Scara'ya da cylindrical robot demiştik değil mi? Doğru
evet,
anladım. Ama
evet.
Scara RRP diye geçiyor. Cylindrical'lar RPP diye geçmiyor muydu? Ben mi yanlış not aldım acaba? Burada Scara'ya RRP demişiz. Bir önceki slide'daki Cylindrical'a biz şey dememiş miydik? RPP dememiş miydik?
Okay. So this is a very good question. Kaan, thank you for the question. Okay.
Şuna bakın
So
hocam.
let me try to explain it. So, you're right. But here, if you put two R's, it also acts like a prismatic joint. So R, for instance, our arm doesn't have a prismatic joint, but we can change the length of our arm. How do we change it? By using two revolute joints. So here, this RR, when you put them together, this is used to change the length of this arm, like we do. So that's why it can make the cylindrical motion.
Anladım. Şey yapıyor. Silindirin length'ini arttırıyor. Aslında yarı çapını arttırıyor sadece oradaki diğer rotation. Dönmediği için.
But in this configuration, you see, this also changes the radius here.
Yes, okay.
This is how we do with our arm. We do not have prismatic joint, but since we have two revolute joints, we can change the radius of our workspace. Okay. Can you see me?
Yes, hocam, I can. Yes, okay.
How I am actually changing the radius. Okay. So two R's also like, so there's one R here, but two R's also act like P.
Okay, and I understand the situation. Okay, thank you so much.
But thank you for the question. This was very important detail. Okay.
Thank you,
So
hocam.
in the cylindrical robot, I need to be able to change my radius. I can change my radius by using two R's. But I also need to rotate. Okay, using any of these R's, I can rotate, surely, like I rotate my arm. And using this prismatic joint here, I can cover the length, the height. So this gives me a cylindrical workspace. So here we show with the question of Khan, I could actually elaborate upon one particular aspect of revolute joint. If you put two revolute joints together, it also acts like a prismatic joint. It enables you to change your radius, as we do in human arm. Okay, here it is the Scar robot. I recommend you write Scar robot into YouTube and watch one of these videos. Okay, articulated robot RRR. Okay, here also we use the same thing. We can use two R's like a prismatic joint to change the radius. Okay. Now, God may also ask, hocam RPR dememiş miydik?
Evet, aynen onu soracaktım ben de tekrar.
Okay, but two of them when come together acts like P. So here we also have effectively RPR effect. So this is the tricky part, an important part, that two R's can also be used as P. Okay, an articulated robot is using in welding, basically spray print painting in automotive industry. It's a very skillful robot. Parallel robot. So parallel robot, the basic difference of parallel robot from the other types of robot is that it's not an open kinematic chain. In the other robot, we see it may have an open chain. For instance, in SCARA, one end is open, end effector. There we put the end effector. Or a cylindrical robot, but here we do not have any open end. So it's a closed chain, we say. Where do we use it? For instance, in all flight simulators, which we use for robot training, pilot training. Parallel robots are used. For instance, here you see a steward platform, this is called, because of the designer's name. The first designer was steward. And this is a parallel robot. You see, it is used that a flight simulator cabin is put on top of this motion platform, and this gives the motion which simulates the motions of an airplane in air. Now the same trick is used here. Airplane also, three airplane has got 6 basic motions. 3 rotations. You can see that 3 rotations can easily be simulated, but how the 3 linear motions can be simulated? And so we have already seen that 2 revolute joints can give the effect of a prismatic joint. But here we have both revolute joints, but also the prismatic joints. Prismatic joints are used to change the lengths of these base links. There are prismatic joints here. So both the lengths of these links, base links, change, and also their angles change. So this is a rather sophisticated design, and it allows us to simulate all the motions of an aircraft in space. So you can look at it closer here. There are joints, revolute joints, and there are prismatic joints. Now, our students in the past made a steward platform and made a miniature flight simulator. And this project in 2014, 2015, almost 9 years ago, won the Best Graduation Project Award. Okay, we have seen the applications in the video segment. And in the past, we had a very good pedigree of robotics. Our students became very, very successful in the international robotic contests. In 2014, about 9 years ago, these were our first graduates, actually. They qualified as the finalist and they participated in Madrid with this robot. So what type of robot is this now? This is a mobile robot. So what was the objective of this robot? This was designed as a guide robot. So to guide the visitors to Central Campus. This robot was recognizing the buildings, and when they come in front of the buildings, it was giving information about the building. So for instance, when it comes in front of the engineering building, it was saying, okay, this is an engineering building, and was giving some short information about the engineering building. Then the following year, we won the second prize. This was again a mobile robot, but this is also a hybrid robot because it has got this this manipulator-like attachment to it. So this is a prismatic joint. This is it can go inside the robot cabin or go outside, and its objective was to make some measurements of air. For instance, you can see here a sensor for measuring the speed of wind. Of course, in order to protect this when we do not use it, this was a retractable arm. So when we do not use it, it could be retracted inside the main cabin of the robot. And the students also gave it a rather nice design. Again, here they used computer graphics to design it first in 3D, gave it a nice environmental color. They called it Ventus. It is a Greek god, which is related to atmosphere. Okay, this design also was very much appreciated. So this is, when you make something like this, now you can call yourself engineer, because you've accumulated a lot of information, you understand this information, and you put it to use to create something of your own in design and also in functionality. Okay, 9 years ago, this is me 9 years ago, with the project leader, Boran Karaduman. It was a very, very successful project, a silver medal. They won, and a prize also, a money prize. This is the project team. The following year in 2016, this time we were in Mexico. This is the Bilgi robotic team in Mexico. And this was a search and rescue robot. It was supposed to make its path planning, as we saw in the shaky robot. This could make the path planning. This could find its path in a rather cluttered environment like this. And it could also find the dolls here, which were simulating the victims after an earthquake. You see, you could find, for instance, a doll here, or here, or here. Looking at the sensors, sensor inputs like heat sensor, the audio sensor, the baby was, these dolls were crying. Also, they were filled with hot water, so they had body temperature. Also, there's the camera. So 3 different ways: by hearing them, by sensing their temperature, or by seeing them. The robots were supposed to find the dolls and rescue them. And how many dolls you could find was the criteria for winning the competition. Okay. The following year, in 2017, this time we were in Brazil, and this time we won the third place and $4,000 of money prize was split between 4 members of the team. These were only split between students. So in this picture, you see the team leader Barnas with the check. This time it is again a hybrid robot. You can see the robot and the manipulator. So this is a hybrid robot. Now, the objective was to clean the park. So robot was expected to see these clutters and move there by using the manipulator, grab it and put it into, it is one of these boxes here, then come back and put them into where the waste bins or garbage bins are going to be. So how many objects you picked in the given time was the criterion for winning, and our team became third. And in 2018, this time we were in Peru. This is the team. And we won the second prize. It is $6,000 of check. You see here, split between the students. And this is their design, Punet. This was an industrial robot. This is again a hybrid robot. Now, once you make a robot like this, it is functioning with all its parts and it is exhibiting intelligence. So it was picking the objects on an industrial floor and organizing them with respect to their colors and going and placing them according to their colors. So altogether, robotics is a combination of mechanics, because the robot has got mechanical parts. It has got sensors, it has got electronics, and it has got a computer. Since he did not have these sensors, electronics, and computer parts, he saw that Leonardo da Vinci could not realize his design in the 16th century. But now, today, after you take this course, your information, of course, combined with the other information accumulated from other courses you've taken so much, enables you to make a robot. And we've proven ourselves that we educate our students enough, and our students are also skilled and intelligent enough to enable them compete in the world platform and win medals in the world platform.